This is Larry Benko, call sign W0QE, and welcome back to part 2 of the RF power combiner video. Yesterday, we learned what we could do within SimSmith to allow SimSmith to be able to analyze circuits with 3 ports or more. Today, we're going to take what we learned in the previous video and apply it to 2 examples. The first example we're going to use is going to be a 2-port Wilkinson power combiner, which we're going to analyze and fool with the components and basically learn a lot about it by being able to treat everything in the combiner as being metered and also be able to be variable. The second example will be an unequal 2-port power splitter that runs on 10 meters. That was an example of a project I did a number of years ago prior to SimSmith for a guy I knew in Arkansas. Hopefully this will be interesting. This circuit, it's already built up, but what it basically is pieces of what we had yesterday plus a power combiner. This is a standard Wilkinson coaxial power combiner. So to review a little bit about from the previous video, I had a generator that powered the ruse block. I sampled the signal here and I terminated the generator. I drove 2 more sources from that generator. Each one of these sources is a 50 ohm output impedance, and using this label and the current through here, I could measure the impedance looking out. And that's done with here I can measure the impedance and put it on a Smith chart. Here I can measure the impedance and plot it as SWR for this point and this point. So I can measure the generator 1 SWR and impedance and generator 2 SWR and impedance. I can plot the wave forms at W0, W1, W2, and W3 if I wish. And I can look at the power in the balance resistor. So a standard Wilkinson combiner, if you're not familiar with them, is a 50 ohm, it's a 3-port device, 50 ohms on all ports. There's lots of Wilkinson combiners and splitters, but this one is a standard 2-to-1. So two sources drive 1 output. We expect the power to be doubled if the losses are low in here. And the impedance of this transmission line is nominally 70.71 ohms. It's so that we transform a 50 ohm impedance to 100 ohm impedance here. And then we have 200 ohm impedances in parallel. The transmission line is 90 degrees in length. And the balance resistor is such that if this load is disconnected, and we'll look at that in a minute, the signal that comes back here gets offset by the balance, so you don't see any effects from generator 1 at generator 2 and vice versa, assuming there's a good impedance out here at the load. So with that having been said, let's look at this circuit a little more closely here. Let's start off at the beginning. It's designed to be a 10 megahertz combiner. So I look at 10 megahertz here on my plot, and I see 2 things. This green scale is the SWR for generator number 2. I turn it off, and this one's laying right underneath of it. It's SWR generator number 1. Those both have a very good SWR, 10 megahertz. Our generator is a 200 watt generator. I'm going to convert this 200 watt generator that comes in here into 2 200 watt generators here. So I would expect my output to be 400 watts, and my output is 400 watts right down here. The reason being that I made the 2 pieces of transmission line, I made them lossless. And for understanding this type of a circuit, it doesn't matter if there's loss in here or not to understand it. We can go back later on and put a real piece of coax in here if we wish. We can artificially add some loss. It doesn't matter. But at the moment, I have 400 watts coming out of my generator. And if I look at the power in my balance resistor, you would expect that to be 0 because these 2 generators both have the same magnitude and no phase difference. And if we go back, that was from yesterday. I'll get there in a second. But if we plot down here at the bottom, probably can't see it. I'll move this up a little bit. The red line here is the power in the balance resistor, and that turns out to be 0 because the voltage here is the same as the voltage here. Voltage and phase are both the same in both cases. So across the resistor, there's nothing. If we, for a moment, just turn SWRs off, and let's look at the waveforms coming in. If we look at W1, which is the output of the first generator, and W2, which is the output of the second generator, and scale the plots accordingly, what we see is a signal that runs up to 141 volts peak. 141 volts peak is a 100 volt RMS signal. A 100 volt RMS signal squared divided by 50 is 200 watts. So there's a 200 watt signal here going into a 50 ohm load, and at W2, there's another one exactly the same. Those two 200 watt signals become a 400 watt signal on the output. And we can look at the output if we want to. There it is. And it's 200 volts peak, which is 141 volts RMS. 141 volts squared over 50 is 400 watts. All right. So the next thing I'd like to do here is let's look at what happens to our SWRs at the generator if we vary the load impedance out here. So let's just vary it. And as I vary the load impedance here, what I see is I see SWR back at both generators. It remains the same for both generators in all cases, but it does vary. And we expect that. I mean, you would not expect the circuit could take care of load changes. So how much does it change by? Let's put a 2-to-1 SWR out here. So we put a 25 ohm load out here. We see the SWR at 10 megahertz being 2-to-1. We put a 2-to-1 SWR out here. That's 100 ohms. Again, we see it's a 2-to-1 SWR at each generator. So that kind of makes sense. What else can we do? Well, we can look at what happens to our power here if we vary our generators. So let's take the generator, the second generator, and change its phase. And let's watch how much the power drops. At a 20-degree phase difference between the generators, our 400 watt output has dropped to 388 watts. That's almost not enough to even worry about. So you really don't need to get the generators phased any more accurately than, say, 20 degrees. What if the generators are not the same amplitude? Let's say this one's amplitude is a little bit lower, this one's a little bit higher. The output now is 400 watts still. Turns out that we get, if they're in phase, we get the sum pretty much of what the powers are, provided they're not, of each generator, provided they're not very large, there's not a large discrepancy in them. You see, if you look down here closely, you'll see that the red line here, which is still near the axis, has moved up a little bit. If we vary this a lot, like, let's move it down this way and move this one up more. Now we start to see the power here. It's still pretty close to 400 watts. We're actually putting more than 400 watts into the circuit. But this power down here is 4 watts. 4 watts into that resistor. So we're losing a little bit, but this is not very much. And this is a large variation in amplitude between the two generators. So that tells me that you really don't need two precise generators here. You need to pay some attention to get the phases right, and you don't want to drive have this generator drive the power combiner through 20 feet of transmission line, and this one drive it through 0 feet of transmission line, or something like that. But if you exercise reasonable care, the phase will be close enough. The amplitudes aren't that important. It acts as a very nice power combiner, which is, that's its goal. So what happens in a circuit like this if we have a fault? Now, if we have a fault, we can say W2, the generator down here, generator number 2, we're going to say goes away. What happens, here's a way to make it go away. I'll just delete that trace. Now it's gone away. Let's look at voltage W2 here and see what happens. Voltage W2 is 0. That's the effect of the balance resistor. And it only works if there's a 50 ohm load out here. If I move the 50 ohm load up or down, we see the red trace there. Didn't get it back to 0. There. If this is a balance, if this is the correct output impedance, This balance resistor compensates for the voltage that comes back this way with an equal and opposite voltage this way. It's 180 degrees out of phase, and the net effect is 0. We don't drive anything back into this generator. And that's, again, a nice thing. You may not need this resistor and you may not care. If your generators are immune to that type of a problem, that's fine. But if you were doing something where this generator and this generator are on slightly different frequencies, and this is something you cannot simulate in SimSmith currently. This is the one small shortcoming. These generators are very flexible, but they both are the same frequency. If I was to drive this combiner for making measurements like IMD measurements, this generator and this generator might be separated by a few kilohertz. A few kilohertz, I cannot separate them in SimSmith at the moment. I'm saying this, and Ward will probably come up in the next version with a way to do it, but at the moment you can't do this, at least to the best of my knowledge. So we're kind of stuck in that case, but that's the reason why you want good balance. Is if these two generators are not exactly the same frequency, the imposing of this generator's signal on this generator's output will cause this generator to produce a little bit of IMD internally. And since we're trying to measure IMD, we don't want that to happen. So in a case of measuring IMD where the two generators are different frequencies, we want an incredibly good balance. As a matter of fact, you might even want to tune this, or you might want to tune the output impedance ever so slightly to really get the balance to be perfect. I've tuned them manually and be able to get this isolation to be down in the order of 65 to 70 dB over the HF range by being really, really careful. Of course, that means then you have to know exactly what this impedance is out here, and it can't vary. But nevertheless, it's doing its job. So this circuit may or may not need this balance resistor. But we can look at this circuit in so many different ways through SimSmith that it's kind of interesting that you sort of develop an appreciation for how the circuit really works. Now, in earlier videos, I did some things along the lines where I replaced a piece of transmission line with some discrete components. We can do that in a power combiner here too. All right, here's an example of the same circuit being replaced with capacitors and inductors, where this C1, L1, and half of C2 is a 3-element pi network that gives me a 90-degree phase shift at 10 megahertz. Now, if we look at our circuit here, we see it's different than before. This circuit has no other frequencies where it actually acts as a power combiner. It only works at the proper frequency. That might be a plus. It's got a narrower SWR bandwidth than the other circuit had. Let me see if the other circuit is still here. Let me see what I can do about moving this out of the way here. Let's close this off. I'll just move this down for a moment. This one here, I didn't mention this before, but if we plot this over a wider frequency range, let's say to 100 megahertz, we'll see that this acts as a 2-to-1 combiner at 10 megahertz, 30 and 50 and 90 or 70, 30, 50 and 70. What we have here is the length of the transmission line is a quarter wavelength, 3/4 of a wavelength, 5/4 of a wavelength, 7/4 of a wavelength. And as long as there's no loss in the transmission line, it operates exactly the same on all those frequencies. The other circuit doesn't do that. And if we look at the SWR on these two, we've got this is hard putting both these on at the same time. This is a little bit narrower SWR bandwidth than this is, but not much. This is a perfectly reasonable solution. And if I was building a 160 meter power combiner, the desire to want to put discrete components in here rises greatly compared to the higher frequencies. On 10 megahertz, we're talking about, let's close this one off again. On 10 megahertz, we're talking about basically 24.5 feet of transmission line. Which brings up an interesting point. What happens if I don't build this properly? Well, if you looked at this closely when I put these numbers up here, you're going to say, where in the heck am I going to get 70.71 ohm transmission line? And the answer is you aren't going to get it unless you might get it on a circuit board if you build it, but you're going to buy 75 ohm transmission line, and that's all there is to it, because that's what's available. When I do that, my SWR, my best SWR at my point where I'm going to operate this circuit is now 1.125. Not bad. And this is what people who build up a Wilkinson combiner get. You can compensate for this with some external components if you wish, and bring the SWR down. We've talked about that a few times before about when you do wiring and stuff like that, bringing the SWR down with some different external series inductor or external shunt capacitor. If we look at the SWR here plotted on the Smith chart, here's what we see. Both of them are the same. Here's the plot with 75 ohm coax, and here's the 10 megahertz point. If we go to 70.71 ohm transmission line here, and 70.71 ohm transmission line here, we see a match at 10 megahertz, which is right here, which is what you expected. So, these little compromises are just the way life works. If you're powerful enough and you wanted to order enough of a product, you could get someone to make you 70 ohm coax. But in reality, you're going to live with this and maybe compensate for it if you wish, maybe not. What happens if I don't get the two links exactly right? What happens then in that case? Well, let me change this topic here real quickly. With 75 ohm transmission line, what do we get for output power? 399. That didn't hurt our output power at all. So this isn't hurting us. The only thing that's causing us a little bit of an issue is the SWR starting to rise. And this power that's dropped here is exactly the amount of power loss you get here due to mismatch loss. And we've talked about mismatch loss before, but it's the way of the world. In this case right here, if we want to, let's say we aren't very accurate, we're going to change our length of our transmission line by 1 foot. Well, it still didn't make much of a change. Our 1.12 to 1 SWRs are still 1.12 for this, and both of them are the same. Nope, they're not quite the same. In this case, the circuit is no longer symmetrical because one of these pieces of transmission line is a little bit longer than the other one. Both SWRs are still quite good, but they're not exactly the same, but we still get good power output. Even if we go the route of making both these pieces of transmission line wrong, we end up with a circuit now that works just fine. It doesn't have its best SWR where we set it to be, but it's not that far off, and we still get good power output. So the length of these pieces of transmission line is not incredibly critical, and certainly anybody who's trying to do this circuit can easily get the length within 1 foot. So it's not super critical. Another thing that you might be a little bit careful about doing. Excuse me. One thing you might be a little bit careful about doing is when you build this circuit up, you need to size this resistor really carefully for fault conditions. So anytime we do anything that imbalances any of these parameters at all along the way, we will start to see there'll be some power down here. So you won't be able to get away with a tiny, tiny little resistor if you choose to include that component. It may not be very big. In this case, the difference in transmission line length didn't affect it hardly at all. It's only a fraction of a watt. But it's something to consider. And faults are something to consider too. If one generator is off and the other generator is on, this resistor sees an awful lot of power. As a matter of fact, if we go back to that case right now that we had before, we just disconnect generator number 2. What we're going to see here is generator 2 is gone, so there's clearly no way that its power can ever make it to the output. We're left with a 200 watt generator. Half of the power pretty much gets to the output, a little bit more than half in this case. It's 106 watts gets to the output, but 94 watts is lost in this resistor. So this has to be sized accordingly. And that's a big resistor if you think you're going to get a fault. All for the ability to have the circuit have good isolation. So a lot of power combiners I built dispense with this resistor. This would have been exactly 100 watts and 100 watts had we had the right values for the transmission line impedances. There they are. Now, I don't know what else I can say about this circuit. We've pretty much beat it up quite a bit, but SimSmith gives you the ability to run through this in a manner that's really pretty amazing. The things you can do, I've still got something wrong here, there we go. The things you can do in SimSmith to analyze a circuit like this and give you an appreciation for what's important is, I can't stress this enough. The ability to, somebody could be out there cutting these two pieces of transmission line and trying to cut them within a hundredth of an inch of each other, and there's just no reason to worry about that. On the other hand, you just don't eyeball it, but you measure it. But if you got it within a couple inches, nobody would ever know the difference. You'd be hard pressed to measure it. So with this being said, again, I can't stress the fact that SimSmith is an incredibly powerful tool. I hope this example has been interesting, and take away from it whatever you think you need. In this example, I will start with an empty SimSmith circuit and build a circuit that I built probably about 10 years ago for a guy I met. I met this guy on 10 meters, and he was part of a net on 10 meters that was comprised of some local guys in the Arkansas area. And he had a vertical and he had a Yagi also on 10 meters. And when he worked the local guys, he always used the vertical, of course. And when the band was open, he would switch back and forth to the Yagi. And I made a comment to him about why didn't he have a power splitter and put some power to the Yagi all the time and some power to the vertical, in which case, you could set the Yagi in the direction you wanted to, and you'd still be able to talk to the local guys at the same time too. And he had no idea how to do that, so I volunteered to help him do that. Anyways, this is a kind of a saga of what I went through to do it, and it's a very good use of SimSmith. At the time I did this, I was not aware of SimSmith. I don't think SimSmith was around then either. But nevertheless, let's start here. Fundamentally, I have one generator, and I want to have two loads. One load will be my dipole, and I'm going to say I want 3/4 of my power going to my dipole, and one load will be my Yagi, and I'm going to say I'm going to put 1/4 of my power to my Yagi. And what I'm going to do here is I'm going to set the frequency initially here to, I'm not sure exactly what frequency it was, but it was somewhere around 28.4 megahertz. It was a little bit above 28.4 megahertz is where they got together. And what we're going to do is we're going to start with a L network here that's going to match a 50 ohm load to a 100 ohm generator. And the reason for that will become apparent pretty quickly. And we can do this with two circuits. We can do this with a circuit that's a low-pass circuit, or we can do it with a high-pass circuit. And the high-pass circuit is the circuit I want to use. Now, if I was to put in parallel at this point right here, another load like this one and another L network like this one, I would have two 100 ohm points in parallel. That would give me a 50 ohm load for the generator. So we have the two values now we need. Let's build that, and let's build it in a ruse block. We can build it in a ruse block in such a manner where we can leave this circuit intact for the moment. We'll get rid of it later. So here's my ruse block. We won't need very much space in the ruse block to build this. And I don't know if you folks like me building the stuff as I do the video, or whether it's better to have it built ahead of time. And some people, I think, appreciate the steps involved, and other people probably think they're redundant. But if you have any comments about that, please let me know. So we will name this this ruse block. We'll call this a 10 meter, say 3-to-1 splitter. What we're going to do in here is we're going to put this circuit replicated twice. So we'll put a capacitor here. Its value will be let's give it a value C1, and we'll give it a Q of 2K. In this case, the Q is just going to be constant, but that's probably not a bad assumption. We're going to give it an inductor here, a shunt inductor to ground. We're going to give it value L1 and a Q. Again, the Q is going to be just a constant Q. We're doing this over a fairly narrow band. And let's connect these things together quickly. Now, if I set the capacitor to the same value I got from the tuner here, set it to 111. Get back where I belong here. 111.4 picofarads. I set the inductor to be 560.3 nanohenries. And let's say it's a Q of 200. And what I'll see if I do that should be obvious. Let's look at the point U1 here, and we'll see that it's 100 ohm impedance, just as we designed the network here to be. Now let's put a second one in parallel here. The second one is pretty simple to put in parallel. We'll just copy this capacitor, Control C, Control V, except it's a different value now, so we'll give it a new capacitance value there. It goes to a load. This load will need to be inside of the ruse block because there's not room outside the ruse block for two loads. And this capacitance will also be 111.4 picofarads. Now at this point in time, I'm starting to get this to be kind of a mess here. If I want to set this up in a manner that I want to control the order at which these things appear, I can do something like this. Say C1 colon C2 semicolon, I mean, L1 semicolon and Q semicolon. Let's close this off. We'll delete these values again. And when it rebuilds these, it'll rebuild these in the right order. Now I'll put our values back in here again. 111.4 picofarads. 111.4 picofarads. Now, the inductor are two 560 nanohenry inductors in parallel, so that becomes a 280.15 nanohenry inductor. And the two inductors in parallel are the same Q. Now for the resistor here, it's not going to be a single resistor. So down here for the resistor, let's put in here R1 plus JX1. That allows us to specify a non-resistive impedance for this load. And there's our two terms. We'll set this to be 50 plus J0 to start with. We'll set this to be 50 plus J0 to start with. Now we should have a match to our transmitter at this point. When we close this off, if I did this all correctly. And there we are, 50 ohms. At this point in time, we can dispense with this. So let's get rid of this, let's get rid of this, and this is our circuit. Nothing to it. So now the next thing we want to do is we want to plot the power at this point. And SimSmith will always plot the power here very nicely for us. So let's go back to the plot window here and put one command in it. We're going to plot, and we're going to give it a name. Let's call it R1.P. It's this component. We're going to measure the power in this component. It doesn't matter if it's a resistor or if it's reactive. It's the way it is. SimSmith will calculate the correct power. It's U1.R1.P. So it's the component, it's the block, the component, and what we want to do with it. And that's what we're going to plot. And we're going to plot that on the power menu. The power menu is the same. I'm sorry. The power axis is the same axis that we plot right here. It's this axis that we plot the normal power from the load in. So what we're going to do here, oh, also I forgot to mention, the guy told me he basically was going to run 1,000 watts. So let's put a 1,000 watt generator in there to start with. So now what I've got here is I can plot the load power at 28 megahertz. I see it's just about 500 watts. I can plot the second load. So I'm plotting both the load here, which let's call this the dipole. We're going to make most of the power go to this one. We'll call this the Yagi. And both of them have 500 watts at the moment. This is kind of what you expected. It's a symmetrical circuit, 1,000 watts in. If it's matched, again, if we can plot the SWR if we want at G here. So let's look at the SWR G. There it is. It's blue. Let's get rid of the blue color and make it something different so it stands out. Let's make it orange. So now SWR is orange, and our Yagi is blue, and our dipole is pink. What we're going to try to do now is adjust these components in such a manner that we get 3/4 of the power going to this port and 1/4 of the power going to this port. So we'll do that by increasing C1 and decreasing C2. We can see right away that things are starting to get go in the right direction. We want to move this up to 750 watts. We want to move this one down to 250 watts, and we want that SWR to be good. And for this example, we're going to make the SWR better than good. We're going to make the SWR like pretty much perfect. I think that's too much capacitance there. Doing this on the fly is a little bit, it's a little bit awkward because it's hard to always get it right. This is looking pretty darn close though. That looks really good. So now the dipole has 747 watts down here applied to the dipole. The Yagi has 249. That's pretty much exactly our 3/4 of the power and 1/4 of the power. The SWR at resonance, as seen by the generator here, is 1.013. I'd call that good enough. Now, at this point in time, this circuit here, if we look at this closely, everybody should recognize this circuit. It's the high-pass T-tuner, which is kind of interesting. This point right here is either the input or the output to the tuner. This is the other one, the output or the input to the tuner. This point normally is not connected. But if you had an old T-tuner that you had at home and you drilled a hole in the back of it, mounted an extra connector right here and wired to the junction between the two capacitors and the inductor, this would be this circuit. And that's exactly what I told the guy to do. And because he had told me he had a whole bunch of tuners floating around, and he put a coax connector in the back of it, wired to here, plugged that into his transmitter, and plugged here into his dipole, and this point into his Yagi, and he went to it. Now, for him to be able to do this, he needed to put a power meter here, he needed to put a power meter here, and he needed to look at SWR back here. But I gave him some starting points on the values, and he said he got it fine. Whether he did or not, I have no idea how close he got it to being right, but he was very happy that it didn't cost him any money to do this, and he could still talk to his local friends when the band was open. He could aim the Yagi in the right direction. So I thought that was pretty cool. So this is a really good example of building something. This is not a typical power splitter. You won't find this circuit anywhere at all. There's no isolation between these two ports to speak of. However, we don't ever generate a signal here that we worry about it coming back out on this port. So this is a really good use of SimSmith. This is the kind of stuff that, in my opinion, we can learn more by using SimSmith than we could by building something. If we do this, we build it, and we check it again in SimSmith when we're done, it really, really enhances your understanding of how things work. But this circuit is the values we get, 187 picofarads, 63, 320 nanohenries. This might be a little bit on the low side for a tuner, so you don't want your tuner to have necessarily some 30 microhenry inductor in it. But if it had a 10 microhenry inductor in it, you could get down to 320 nanohenries pretty easily. The loss in the circuit is very low. If we want to look at the loss in the inductor here, well, it's easy enough to do it this way. It's 747 watts, 249. That's 4 watts less than 1,000. So the inductor has 4 watts in it. We can see if we change the Q of the inductor, we can see the curves both coming down a little bit. But a Q somewhere in the 50 range still leaves me with 737 watts and 245 watts. That still is not very much power in the inductor. So this circuit represents, in my opinion, it's the kind of stuff that showcases how SimSmith is really practical. Trying to do this in LT Spice and adjust the component values and see what you got and readjust them and scan them and sweep them is so much more difficult than it is in SimSmith that SimSmith just makes this problem incredibly easy. It's unfortunate that it's hard to get people to understand this and be able to show it to them, but once they do see it, it seems like it's like, wow, that's really cool. So I hope everyone's enjoyed this example.